Before we start, hit that subscribe button and give this video a like. It helps us keep making content like this. Now, let me tell you a story that will change how you see the night sky. November 5th, 2018. Inside NASA's Jet Propulsion Laboratory, the mission control room went dead silent. Engineers stared at their screens, watching data that had taken 16.5 hours to reach Earth. It came from Voyager 2, the most distant, loneliest human-made object still working. And what the readings showed made no sense. Plasma sensors, ancient instruments built back when disco was king, suddenly spiked. The temperature of the surrounding environment jumped to tens of thousands of degrees. Particle density shot up like the craft had hit an invisible concrete wall. But there was no wall out there. No star, no planet. Just eternal blackness billions of kilometers from home. First, everyone thought it was a glitch. Voyager 2 had been flying for over 40 years. Its computer memory is millions of times smaller than your phone's. The systems are worn out. Its nuclear heart is dying. But when they double-checked the data and compared it with readings from Voyager 1, which had passed through the same region 6 years earlier but at a different location, the truth hit them. This was no malfunction. Voyager 2 had crashed into something real. It had reached the very edge of our solar system, the border where the sun's power ends and the unknown, hostile ocean of interstellar space begins. We usually think of space as empty, a perfect vacuum where you could fly forever without touching anything. But the data from our cosmic frontier shatters that illusion. The solar system isn't open territory. We live inside a giant bubble, sealed on all sides, and the walls of that bubble aren't a metaphor. They are made of raging, superheated plasma, a wall of fire and radiation that separates us from the rest of the galaxy. Today, we're going to dive deep into that incredible journey. What exactly did the Voyagers see when they punched through that wall? Why do scientists call this zone a firewall? Where does 30,000 heat come from when there's no heat source nearby? We'll also learn why the true shape of our home isn't a sphere, but something closer to a squashed croissant or a damaged insect. And finally, we'll answer the most unsettling question. What lies beyond that wall? Are we truly trapped inside a local bubble? And is something out there in the dark, watching us? To understand what happened at the edge of the solar system, we need to rewind to the mid-20th century. Humanity was just learning to crawl beyond Earth's atmosphere. Rockets exploded on launch pads. Satellites tumbled back to Earth. Nobody was thinking about interstellar flight. But in 1965, a young intern at JPL named Gary Flandreau made a calculation that changed everything. He was plotting the orbits of the giant planets Jupiter, Saturn, Uranus, Neptune, and noticed a strange alignment. Once every 176 years, these four giants line up in a long, curved arc. A rare planetary parade. Flandreau realized that if NASA launched a spacecraft at exactly the right moment in the late 1970s, it could perform a grand tour, fly past all four planets using each one's gravity as a slingshot. A gravity assist lets a spacecraft steal a tiny bit of a planet's orbital energy, catapulting it toward the next target. Without that trick, a trip to Neptune would take 30 years. With the alignment, only 12. This was a once-in-a-lifetime chance. If NASA missed the 1977 launch window, the next opportunity wouldn't come until 2153. None of us would be around to see it. So the decision was immediate. We go. They built twin spacecraft, Voyager 2 and Voyager 1. The names can be confusing. Voyager 2 launched first, on August 20th, 1977, but Voyager 1 took a faster trajectory and soon overtook its brother. These machines were the pinnacle of 1970s engineering. Each weighs about 722 kilograms. It has a white dish antenna 3.7 meters wide to talk to Earth. It has eyes or television cameras on a movable platform. It has ears, plasma wave receivers. And it has a heart, 3 radioisotope thermoelectric generators. No solar panels out there, sunlight is as faint as a distant star. Instead, Voyagers run on the decay of plutonium-238. At launch, they produced about 470 watts, less than your microwave oven. On that tiny amount of power, they had to run a computer, heat their instruments, turn their cameras, and shout a signal across the abyss. Think about the technology. Voyager's computer system has just 68 kilobytes of memory. One photo on your phone is 1,000 times bigger than the entire memory of this ship. Data was recorded on an 8-track tape recorder. If the tape snapped or jammed, the mission would be over. The transmitter puts out 23 watts, the power of a refrigerator light bulb. With that whisper, Voyager had to scream across billions of kilometers. The flight to Jupiter took nearly 2 years. In March 1979, Voyager 1 approached the king of planets. Until then, Jupiter was just a blurry striped blob in telescopes. Voyager showed us a churning, dynamic world. It saw the Great Red Spot, a hurricane 3 times the size of Earth that has been raging for centuries. It saw complex atmospheric vortices spinning in opposite directions. But the biggest surprises were waiting on Jupiter's moons. Io, a moon the size of our own, turned out to be the most volcanically active body in the solar system. Right before the scientists' eyes, Voyager photographed volcanoes blasting sulfur hundreds of kilometers high. That shattered the old idea that moons were dead rocks. Then came Europa, a smooth ice ball crisscrossed with cracks but almost no craters. That suggested a vast liquid water ocean beneath the ice, containing more water than all of Earth's seas combined. For the first time, we had hints that life might exist not only on planets but in the frozen deeps of distant moons. After a gravity boost from Jupiter, the Voyagers shot toward Saturn. The encounters happened in 1980 and 1981. Saturn, Lord of the Rings. Voyager showed that the rings aren't solid disks but thousands of thin threads made of ice boulders and dust. They even saw shepherd moons, tiny satellites whose gravity keeps the rings in line. But at Saturn, the twins' paths diverged. NASA had a choice. Voyager 1 could fly onto Pluto, but that would mean skipping Titan, Saturn's mysterious moon, the only moon with a thick atmosphere. Scientists chose Titan over Pluto. They sent Voyager 1 on a risky close approach, just a few thousand kilometers from Titan's orange haze. It didn't see the surface, but its sensors analyzed the atmosphere and found organics. Methane, ethane, complex hydrocarbons. Titan was a factory of prebiotic chemistry, a frozen version of early Earth. After that maneuver, Voyager 1 shot upward, perpendicular to the plane of the planets. Its planetary mission was over. Now it was headed into black emptiness, away from everything known. It became a lonely wanderer, its only goal to fly as fast and as far as possible. Voyager 2, however, continued the grand tour. It still had Uranus and Neptune ahead. In January 1986, it flew past Uranus, a strange pale blue world rolling on its side like a wounded animal. Uranus looked calm and boring, but its magnetic field was insane, tilted wildly and offset from the planet's center. Voyager 2 discovered new moons and rings no one had suspected. Then, August 1989, Neptune, the final frontier, the farthest planet. Pluto was still considered a planet then, but it's small and far away. Neptune greeted Voyager with storms. Scientists saw a great dark spot, a giant hurricane where winds scream at 2,000 kilometers per hour, the fastest in the solar system. Voyager flew past Triton, Neptune's largest moon, and found geysers of liquid nitrogen. Imagine -235 degrees Celsius and fountains of nitrogen shooting up, instantly freezing and falling back as black snow. With that, the planetary part of the mission ended. Both probes had performed 1,000% beyond expectations. They discovered dozens of new moons, explained the nature of rings, shown us volcanoes and oceans where we expected only ice and rock. By all logic, the program could have been shut down. Funding was cut. Many engineers retired or moved to new projects. But Voyagers didn't die. Their nuclear hearts kept beating. And so a new mission began, the Voyager Interstellar mission. The goal? Find the edge. Find where the sun ends. The 1990s and 2000s were the Great Silence. The probes were receding at 17 kilometers per second. Communication became harder and harder. To catch their voice, Earth had to combine giant antennas from NASA's Deep Space Network into one system. All this time, they were flying inside the Heliosphere, the bubble of space dominated by the sun. Our star isn't just a light bulb. It's a fusion reactor that constantly spews millions of tons of matter. That flow is the solar wind, protons, electrons, alpha particles. It blows at 300 to 800 kilometers per second, inflating a giant bubble that pushes back against the interstellar medium. As long as Voyagers were inside that wind, they were home. But scientists knew that eventually the solar wind's pressure would weaken. It would balance with the pressure of interstellar gas pushing from outside. That balance point is called the termination shock, the first line of defense. Voyager 1 reached it in December 2004, at 94 astronomical units from the Sun, about 14 billion kilometers. Its instruments showed the solar wind suddenly slowing down from supersonic to subsonic. Imagine a supersonic jet slamming on its brakes. A shock wave forms. Plasma heats up. The magnetic field turns chaotic. Voyager had entered the heliosheath, the meat between the bone and the skin. There, the solar wind no longer flows smoothly. It swirls, mixes with particles leaking in from outside. It's a zone of turbulence. Voyager 1 flew through that chaos for 8 long years. Then came 2012. The data began to show something strange. The number of particles coming from the Sun started dropping, first slowly, then in jerks, up and down. The probe was like a swimmer at the edge of the surf, diving into waves. On August 25, 2012, all instruments recorded the final change. The solar wind vanished completely. Zero. Silence. Instead, detectors were flooded with galactic cosmic rays, ultra-high energy particles accelerated by supernova explosions and black holes somewhere deep in the Milky Way. Their intensity shot up many times. That was the moment of truth. Voyager 1 had crossed the heliopause. It had left, but there was confusion. The data didn't match theoretical models. Scientists expected that when you exit the bubble, the direction of the magnetic field would change. Because inside, the field is dictated by the Sun. Outside, by the galaxy. They should point differently. But Voyager 1 didn't see any change in direction. The field strength went up, like a tightened guitar string, but the compass needle didn't budge. For years, skeptics argued, it hasn't really left. It's still in some weird pocket of the heliosphere. They proposed a magnetic highway, where solar and galactic field lines tangled together. Voyager 1 was just traveling down that highway, still in the foyer. They needed confirmation. They had to wait for the second scout. Voyager 2 was 6 years behind and on a different southerly trajectory. When Voyager 2 reached the border in 2018, it ended the debate. Its crossing was sharper, more dramatic. In a single day, the readings changed radically. And unlike its twin, Voyager 2 still had a working plasma spectrometer, the instrument that had failed on Voyager 1 back in 1980. Thanks to that working instrument, we could directly measure the temperature and density of the medium. And that's when we discovered the wall of fire. Voyager 2 sensors showed that just beyond the heliopause, the plasma temperature ranges from 30,000 to 50,000 Kelvin. That sounds absurd. Isn't space absolute zero? Minus 273 degrees Celsius? How can there be such heat like inside a nuclear reactor? Here's the key. In space, heat and temperature are different. On Earth, if you stick your hand in a 200-degree oven, you'll burn because the air is dense, billions of molecules hit your skin every nanosecond, transferring energy. In interstellar space, the vacuum is nearly perfect, maybe 1 or 2 particles per cubic centimeter. Temperature in physics measures the kinetic energy of those particles, how fast they're moving. Out there, particles scream at insane speeds, so their formal temperature is tens of thousands of degrees. But because there are so few of them, they can't transfer heat to a spacecraft. If you stuck your hand out of Voyager, you wouldn't burn, you'd instantly freeze. The ship continues to cool even while flying through roasting plasma. So why are those particles so fast? Where does the energy come from? It's the result of 2 worlds colliding. The solar bubble isn't just hanging in emptiness. It's moving, and it's crashing into the interstellar wind. At the collision zone, plasma gets compressed and heated, like a wave of water piling up in front of a speeding ship. Voyagers punched through that wave. This discovery proved that our solar system is surrounded by a hot, protective shell. We are like a yolk inside an egg, surrounded by white. The shell acts as an extra filter. Without it, the amount of galactic radiation reaching Earth would be even higher. That wall of fire burns away some of the most dangerous particles, keeping them out. We owe that wall a debt of gratitude. But the wall of fire is just the tip of the iceberg. Data from the Voyagers and their colleague IBEX, which scans the boundary from Earth orbit, over the last 5 years have forced us to completely redraw the shape of our home. If you open old astronomy textbooks from the 1990s or 2000s, you'll see the heliosphere drawn as a comet, a round head containing the Sun and planets, and a long tail stretching billions of kilometers behind. That seemed logical. We're flying through the galaxy, so there should be a wake. But reality turned out to be far stranger and more chaotic. In 2020, a team of astrophysicists led by Merav Ofer at Boston University used new Voyager data to build a refined 3D model. When the computer finished rendering, they didn't see a comet. They saw a deflated croissant, or, if you like, a giant shell-less prawn. Our heliosphere has no long tail. It's squashed. It has two short, curved lobes at the back, with a gap between them. Why is the shape so ugly and irregular? Why does our protective bubble look like something took a bite out of it? The answer lies in an invisible battle of magnetic fields. The sun is not just a source of light and wind, it's a giant magnet. And because the sun rotates once every 27 days, its magnetic field gets twisted into a spiral, like a ballerina's skirt. That magnetic skirt reaches all the way to the edge. But outside, there's also a magnetic field, the galaxy's own field, and it pushes against our bubble with monstrous force. That external field crushes the tail, preventing it from stretching out. It deforms our shield, flattening it from the sides. This discovery is unsettling because of its instability. We thought we lived in a perfect sphere, but we actually live inside a pulsating, distorted bag that constantly changes shape under the blows of galactic waves. And that bag has holes. Voyagers discovered a process called magnetic reconnection, where solar magnetic field lines break and reconnect with galactic field lines, creating tunnels, cosmic highways through which matter can flow freely in and out. Our quarantine isn't perfect. The galaxy keeps feeding us its material, and we don't always know what comes through those open windows. Now let's talk about why the pressure outside is so strong. Why the external environment attacks our bubble so aggressively. In 2020, while analyzing Voyager 2's data, scientists noticed another counterintuitive anomaly. Usually, we think that the farther you get from a star, the emptier space becomes. Inside the system, there's lots of dust, gas, solar wind. Outside should be a perfect vacuum. But the instruments showed the opposite. As soon as Voyager 2 left the heliosphere and flew a little farther, it recorded a rise in electron density. The plasma density outside turned out to be higher than inside the thin solar wind. We flew to freedom into thick fog. It's like a submarine that surfaces from the deep only to find the water above even denser. This confirms that the solar system is currently passing through what's called the local interstellar cloud, a giant clump of gas and dust about 30 light-years across. We entered it roughly 40,000 to 60,000 years ago, a blink in cosmic time, and we'll keep flying through it for another 10,000 or 20,000 years. Where did this cloud come from? It's the ashes of a graveyard. We live in a region of the galaxy called the local bubble, a huge cavity in the interstellar medium hundreds of light-years wide. That cavity was carved millions of years ago by a series of catastrophic supernova explosions. Imagine 10 or 15 massive stars blowing up one after another like a chain reaction. The shock waves from those blasts swept all the gas out of this region, creating a bubble of hot, thin gas. The local interstellar cloud that we're now sailing through is a clump of material that never got blown away, a leftover shred of those ancient explosions. It consists of hydrogen, helium, dust, and traces of heavy elements born in the nuclear fire of dying stars. We are literally breathing the ashes of our stellar ancestors. That cloud is what creates the pressure that squashes our heliosphere into a croissant and builds the wall of fire at the border. We are flying through resistance. And that brings us to the most alarming scenario astrophysicists warn about: the galactic winter. We're used to stability. We think the sun shines the same every day, and space around us never changes. But the solar system is a bullet moving at 230 kilometers per second around the galactic center. Along its path, it encounters different weather conditions. Right now, we're in a relatively thin cloud, but what happens if we fly into a really dense nebula? Voyager data allows us to model that. If the density of interstellar gas increases 100-fold or 1,000-fold, and such clouds do exist on our trajectory, the pressure on the heliosphere would become catastrophic. Our bubble would shrink. First, the boundary that Voyagers crossed at about 120 Australian dollars would be pushed inward toward Pluto's orbit, then toward Uranus, then Saturn. If the compression continued, the heliosphere could shrink all the way to Earth's orbit. What would that mean for us? We would lose our shield. Galactic cosmic rays, lethal radiation, dust particles, would flood into Earth's atmosphere. The ozone layer would be destroyed. Background radiation on the surface would spike, causing mutations and cancer. The climate would change. Dust in the atmosphere would block the sun. Geologists have found traces of iron-60 isotopes in Antarctic ice cores, iron that could not have come from natural processes on Earth. That iron came from space, from supernovae. That means Earth has lost its shield before. Some scientists link those periods to global extinctions and ice ages, when our planet turned into a white snowball, a snowball Earth. The Voyagers are our only sentinels, our weather balloons. They're out there on the front line, measuring the density. So far, they're telling us, density is rising, but it's still tolerable. They're letting us know that, for now, there's no storm ahead that could wipe out civilization. But we don't know what will happen in 1,000 years of flight. In 2021, while continuing to listen to the radio environment around Voyager 1, scientists at Cornell University found another anomaly, something that made them shiver. Normally, the interstellar medium is quiet. Spikes of activity happen only when the sun launches a coronal mass ejection. The shock wave from the sun reaches Voyager about a year later, hits the surrounding plasma, and the plasma rings like a bell. Instruments record a sharp beep. But this time, the sun was calm. No outbursts. Yet Voyager still heard a sound. Not a sharp beep, but a monotonous, constant low-frequency hum. Imagine a quiet, barely audible rain tapping on a roof, or the noise of static electricity. This hum never stopped. Scientists concluded, that's the voice of the plasma itself. Interstellar gas is vibrating. It's in a constant, low-level excitation. This discovery was revolutionary. It proved that the void beyond our system isn't dead silence. It's a living, dynamic medium where unknown processes are at work. Voyager is hearing the breathing of the galaxy. The hum is very faint, at the edge of the instrument's sensitivity, but it's there, and it's everywhere. It changes our perception. We're not hanging in nothingness. We're sailing through an ocean that makes noise, and that noise tells us about pressure, about hidden energy permeating the space between stars. Now let's shatter the most popular myth about Voyager. You've seen headlines, Voyager has left the solar system. That sounds proud. Humanity has beaten gravity and escaped its home. But astronomers just shake their heads. Technically, the Voyagers have left the Heliosphere. They've stepped out the front door of the house. But they haven't even reached the garden gate. The gravitational boundary of the solar system is terrifyingly far away. Let me put it in perspective. Imagine the solar system as a football field. The sun is a small coin in the center. Earth is a grain of sand a few centimeters away. Neptune's orbit is about the penalty area. The Voyagers are currently somewhere near the goal line. They've flown that far. But the sun's gravitational domain isn't the football field. It's the entire city the stadium sits in. Far beyond the planets, in the cold dark, lies the Kuiper Belt, a collection of icy bodies including Pluto. Voyagers are already inside that. But even farther begins the Oort cloud. It's a giant spherical shell made of trillions of icy comets, drifting slowly around the sun, barely held by its gravity. That's the true edge. Let me give you numbers that make your head spin. Distance from Earth to Sun, 1 astronomical unit, AU. Voyager 1 has flown 162 Australian dollars. The inner edge of the Oort cloud starts at about 2,000 Australian dollars. The outer edge ends at roughly 100,000 Australian dollars. Do you see? It's flown 160. It needs to fly 100,000. If Voyager keeps its current speed, and it will because there's no friction in space, it will take another 300 years just to reach the beginning of the Oort cloud. To fly all the way through and truly, permanently, irrevocably leave the solar system, to escape the sun's gravity, it will take 30,000 years. 30,000 years. Let that sink in. 30,000 years ago, Neanderthals were still alive on Earth. Homo sapiens had just begun to paint on cave walls. There were no pyramids, no will, no writing. That same amount of time must pass into the future for this small piece of metal to break free. By the time Voyager exits the Oort cloud, humanity might be gone. Our cities turned to sand. Our languages forgotten. Perhaps we'll evolve into cyborgs or destroy ourselves in nuclear war. And it will still be flying in absolute silence, among icy boulders, in total darkness. This is a real prison. We're locked in not by a plasma wall, but by space itself. Distance is the most reliable jailer. Even light takes more than a year to reach the Oort cloud. The nearest star, Proxima Centauri, is 4 light-years away. For Voyager, a trip to the nearest star would take 40,000 years. And by the way, it's not heading toward Proxima. Voyager 1 is aimed at the constellation Ophiuchus. In 40,000 years, it will pass within 1.7 light-years of a star called Gliese 445. Just pass by, it won't stop or orbit. It will shoot through that system and keep going into infinity. Voyager 2, after the same 40,000 years, will pass near the star Ross 248, and after 296,000 years, it will pass near Sirius, the brightest star in our night sky. Almost 300,000 years of flight. By then, geological epochs will have changed on Earth. Continents will have shifted, and it will still be flying. That level of loneliness is something the human brain cannot truly grasp. We have created things that are immortal compared to us, and that brings us to the most touching, philosophical part of this story: what the Voyagers carry. But before we talk about eternity, let's return to the present. Right now, at this very second, the Voyagers are dying. A slow, agonizing death by starvation. Their radioisotope generators are inevitably degrading. Plutonium-238 decays. Heat diminishes. Thermocouples wear out. We lose about 4 watts of power each year. That sounds small, but when every watt counts, it's a death sentence. Currently, each probe has less than 250 watts left. That's not enough to power all systems. NASA engineers are forced to play a cruel game. They must choose which organ to amputate so the brain can keep living. First, they turned off the cameras of Voyagers went blind in the 1990s. No more photos. That hurt, but it was necessary. Cameras consumed too much. Then they began turning off heaters for scientific instruments. That was a huge risk. The instruments were designed to work at room temperature or at least mild cold. Without heaters, temperatures inside the hull dropped to -50 or 60 degrees Celsius. Everyone thought the instruments would die, lubricants would freeze, circuit boards would crack. But to everyone's amazement, the cosmic ray and plasma detectors kept working. They became icy zombies, functioning against all specifications. That's a testament to the genius of 1970s engineers. They built things to last forever. But you can't cheat physics. Power keeps falling. In 2023, NASA performed a hack. They sent a command to Voyager 2 to disable a voltage protection circuit. That allowed them to tap a small reserve of energy that had been saved for emergencies. It's like drinking the last canteen of water in the desert. It will extend the instrument's life another couple of years. Maybe until 2026. What then? Then the cascade shutdown begins. First, the plasma detector will fall silent, then the magnetometer, then the low-energy particle detector. By around 2030, maybe 2032 at the latest, the last scientific instrument will go dark. Voyager will stop being a scientific tool. It will stop sensing the cosmos. But it will still be alive. This transmitter will keep working. It will send back only a carrier tone, a simple signal. I'm here. I'm alive. Then there won't be enough power for even that. The transmitter will fall silent. Or, more likely, the probe won't have enough energy to keep its antenna pointed precisely at Earth. The signal beam, thin as a needle, will drift away, and we will lose it forever. It will become a dead lump of metal, drifting among the stars. But in a strange way, that's when its main mystical mission will begin. On board each Voyager, mounted prominently, is an aluminum cover. Under it lies a legendary object, the Golden Record. It's a 12-inch copper disc plated with gold to protect it from cosmic corrosion for billions of years. Along with the disc are a stylus and a cartridge for playback. And on the cover is engraved an instruction manual, a language based on physical constants that any advanced civilization should understand. The hydrogen atom's transition frequency, a map of pulsars locating our sun. So what did we choose to tell the universe about ourselves? If you find this disk a million years from now, what will you think of the beings that made it? The selection was led by the legendary Carl Sagan. They had only a few months to compress all of Earth's history, culture, and biology onto one copper disk. There are 118 photographs, not digital files, but analog signals encoded as sound. To see the images, someone would have to play the record and decode sound waves back into pictures. There are photos of the planets, diagrams of human anatomy, a man and a woman, though NASA, due to 1970s Puritan censorship, only allowed silhouettes. There are pictures of food, architecture, animals, an airplane, a train, an X-ray. But the most important part is the sound, the audio landscape of Earth. The authors recorded sounds we take for granted but that define our lives. Rain, wind, a crackling fire, a train, a kiss, a baby's cry and a mother's soothing voice, a dog barking. There are greetings in 55 languages, from ancient Sumerian and Hittite to modern Russian, English, and Mandarin. Short phrases, hello, star travelers, wishing you peace, and of course, music. Music is the universal language of emotion. The choice was agonizing. How do you pick 27 tracks to represent all of humanity? There's Bach, Beethoven, Mozart, Stravinsky, but also Louis Armstrong's jazz, Blind Willie Johnson's blues, Chuck Berry's rock and roll. There's folk music, Pygmy Girls songs from Africa, Peruvian panpipes, Azerbaijani mugam, Georgian choral singing. It's an eclectic, strange, incredibly alive playlist. But there's something even more intimate on the disc. Andrew Yen, the creative director of the project, who would later marry Carl Sagan, proposed recording the electrical activity of a human brain and heart. She hooked herself up to an EEG and thought about Earth's history, the horrors of Nazism, poverty, but also about love. At that moment, she had just realized she was in love with Carl Sagan. That electrical imprint of a woman's brain, in love, is now engraved on gold, flying through interstellar darkness. That might be the most romantic gesture in history, an electrochemical love signal that will outlive Earth itself. But there's a dark side to this metal. On the cover of the record, beside the playback instructions, is a map, a pulsar map. It shows our sun at the center, with lines radiating out to 14 pulsars, neutron stars that spin at freakish speeds and emit radio pulses as precise as atomic clocks. Next to each line, binary code encodes the pulsar's frequency. Any advanced civilization that finds it can use those pulsars as galactic lighthouses, triangulate, and pinpoint exactly where our solar system is. Moreover, because pulsars slow down very gradually over time, they can also calculate exactly when the spacecraft was launched. We literally drew an arrow saying, "We are here. Come visit." Many scientists, including Stephen Hawking, criticized this decision. They called it madness. Hawking warned, "Meeting a more advanced civilization might be for us what Columbus's arrival was for Native Americans." That didn't end well. We assume that higher intelligence must be kind and humane. But evolution on Earth teaches us otherwise. The strong survive, predators eat prey, and a technologically more advanced civilization almost always absorbs or destroys a less advanced one upon contact. This brings us to the dark forest theory, described by science fiction writer Liu Cixin but with serious scientific grounding in the Fermi paradox. Imagine the universe as a dark forest. Every hunter stalks silently, trying not to be seen, because in the forest there are other hunters. If a hunter sees movement, they shoot without hesitation to eliminate a potential threat. In such a forest, silence is survival. Shouting, "I'm here," is suicide. Maybe that's why the cosmos is silent. Not because no one is out there, but because everyone else is smart enough to stay quiet. Everyone who shouted has been destroyed. And we just sent 2 shiny spacecraft with precise coordinates of our home straight into the heart of that forest. Plus, we've been carelessly blasting radio signals into space for over a century. The Voyagers are our naive, childish attempt to make friends. We're reaching out into the dark, hoping for a handshake, not a bite. But what's done is done. Voyager 1 can't be stopped. It's flying away at 17 kilometers per second. The map is sent. And even if it was a mistake, it was a magnificent mistake, born of hope, not fear. On February 14, 1990, when Voyager 1 had finished its primary mission and was speeding toward the edge, it was 6 billion kilometers away, far beyond Neptune's orbit. Carl Sagan convinced NASA to take one last picture. It was technically difficult. They had to turn the camera platform back toward the sun. There was a risk that the sun's bright light would burn out the optics. Engineers resisted. Why waste precious time and power on a photo of nothing? There's nothing to see anymore. But Sagan insisted. Voyager took a series of images that became the family portrait of the solar system. In one of those images, in a scattered ray of sunlight reflecting off the camera optics, you see a tiny, barely visible dot. That dot is less than a pixel, 0.12 pixels. That's Earth. Looking at that image, Sagan wrote words that became perhaps the most powerful philosophical manifesto of the space age. Listen to them. Imagine the picture. Huge, grainy emptiness, and one little speck of dust. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That photograph destroys our ego. Think of the rivers of blood spilled by generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of that dot. Think of the endless cruelties inflicted by the inhabitants of one corner of that dot on the barely distinguishable inhabitants of another corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturing, our imagined self-importance, the illusion that we have some privileged position in the universe, all of it is humbled by this pale point of light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Voyagers gave us more than scientific data about plasma and magnetic fields. They gave us a mirror. They flew so far away so that we could turn around and truly see ourselves for the first time. See how fragile we are. The wall of fire at the system's edge protects that dot, but it also isolates it. We are alone, at least for now. So what awaits them? As we said, in a few years they will fall silent forever. Their thermal hearts will cool. They will turn into icy lumps of metal. But in space, death isn't an end. It's a transition to another state. In a vacuum, there's no oxygen to rust the metal, no moisture to cause corrosion, no wind to erode the surface. The only enemies are micrometeoroids and cosmic dust. They will slowly, atom by atom, wear down the Voyagers' hulls. But that process will take millions of years. The golden record is under an aluminum cover, well protected. Calculations show that erosion won't erase the information on the disk for at least 1 to 2 billion years. A billion years. In 1 billion years, the sun will be about 10% brighter. Earth's oceans will begin to boil. Life on the surface will become impossible. Our planet will turn into a scorched desert like Venus. Humanity will probably be long gone. Either we will have left for the stars or vanished. And the Voyagers will still be flying. They will outlive our civilization. They will outlive our biosphere. They will even outlive the sun itself. In 5 billion years, the sun will swell into a red giant, swallowing Mercury, Venus, and probably Earth. Then it will shed its outer layers and shrink into a dim white dwarf. The solar system will die, but the Voyagers will already be far away. They will orbit the center of the Milky Way once every 225 million years. They will become eternal monuments to the fact that once, around a yellow star, there lived a civilization that managed to overcome gravity, that was brave enough to send a message into nowhere, and loving enough to include the sound of a kiss on that message. Maybe billions of years from now, when the galaxy is completely different, some alien ship will intercept this strange ancient artifact. They will bring it aboard. They will see the diagram. They will place a stylus in the groove. And in the silence of their cockpit, a voice will speak in a dead language, "Hello, children of planet Earth," and Chuck Berry's music will play. And for those few minutes, we will be alive again. The story of Voyager is not just about technology. It's about breaking boundaries. First, we broke Earth's gravity. Then we broke the asteroid belt. Then we broke the sun's pull. And finally, we broke through the heliopause, that very wall of fire. We humans are explorers. No cage can hold us. Right now, as you watch this video, Voyager 1 is more than 24 billion kilometers away. A radio signal from there takes 22.5 hours to reach us. The light you see from stars is ancient, but the darkness through which Voyager flies is even more ancient. It is paving the way. Perhaps, thousands of years from now, warp-drive ships will follow its trail. And the passengers of those ships, as they pass the coordinates where the ancient probe drifts, will salute it. But there's one question that haunts us. If we could send ships beyond our bubble, if we could announce our existence, why hasn't anyone done it before us? Why, despite billions of stars in our galaxy alone, have the Voyagers encountered only silence and plasma? Where is everybody? Why is the dark forest so quiet? And is there really anyone out there in the dark? Or are we the only intelligent beings for millions of light years, locked inside a squashed croissant of a heliosphere? That question, the Fermi paradox, deserves a deep, chilling conversation of its own. That's what we'll explore in our next video. We'll break down theories that will make your blood run cold, from the zoo hypothesis to the great filter. If you don't want to miss that, subscribe and hit the bell. For now, look up at the night sky and remember, out there in the infinite distance, a small piece of us is still flying. Thanks for watching.